Hi guys, in the last episode we have learned how to build a static node graph. What is static node graph? It's a node graph where the nodes are all known at the compile time, all the connections are known at compile time, and in our case it has been built on the stack. So you can see our nodes, transfer node, source node and target node, they are created here in the main function scope. They are created on the same stack frame, so they have same lifetime. They will all live a same amount of time. This means that if you look at the references between them, so for example, this pin here is referencing this pin here, there is an arrow here, and this pin here is referencing this pin here, right? So I can show you in the code. So you have a pin here, and this pin T connection is the opposing pin, right? So every pin will have M connection opposing pin. So for this pin, M connection will be this pin, right? And for this pin, M connection will be this pin. So this is like a cycle here going on. So what will happen if one of these nodes was to disappear, during the runtime? What would happen is this pin would disappear because it's a member of this node. And then this reference here would become invalid. So this pin here would be pointing into somewhere where it shouldn't, right? It will be a dangling pointer, and we don't like that. So in case of a static node graph, it's not a problem because this node will never disappear while this one stays alive. If this one is going to go, this one is also going to go, and this one is also going to go because they are all in the same stack frame. So you can see that by defining them in this one function all together in one stack frame, their lifetime lasts the same amount of time, So when we create connection here between them, this connection will stay valid for the lifetime of those nodes because they have common lifetime. Right. What are the features of this static node graph? So you can see that the base class node has a protected destructor, but it also has virtual methods. So it's kind of interesting because you have destructors that's not virtual, but you do have virtual methods. So there is some runtime polymorphism going on, but the destructor is protected as it's not virtual, okay? What else is very interesting here? You can see that the nodes inherit the node interface privately. So this is private inheritance because the default visibility scope for class is private, right? If it was struct, it would be public, but this is class, so this is private inheritance. And this means that if I have an instance of a source node, I cannot substitute a reference to a node with my source node. Okay, same with target node, it's private inheritance, and this one is also private inheritance. And this is all possible, right? So we have non-virtual protected destructor, and we have private inheritance. How does that even work? It works because the types of the nodes are known at compile time. We know the types. When these nodes are created here on the stack frame of the function main, they all get dropped at the end of the stack frame, right? So the destructors are called for those particular types. So transform node will have transform node destructor call because compiler knows that this is a transform node. It doesn't need virtual destructor, okay? So even though transform node inherits node privately, it has a destructor, and this destructor is public. So the destructor of a concrete class transform node is public, and the destructor of the node, which is privately inherited by transform node, that destructor is protected. So the destructor of transform node can call the destructor of the node because it has access to protected members of the node. The outside world will not have access to the destructor of the node, and it will not have access to the node either. We can see that we're calling the node methods process forwards and process backwards on source node and target node. These are virtual methods in the node. An user cannot call the virtual methods of the node on the source node, because source node inherits node privately, so those methods are private in the source node. However, they are implemented as public, okay? So user will be able to call the public version of these methods, but this will be non-virtual version. So when user calls process forwards, it is a non-virtual call. If there is some hidden user having a reference to source node which is node reference, then they will be calling them virtually, and we'll look into that in a second. Same applies to the target node. It inherits node privately. it overrides those virtual methods. So they are, the virtual methods are inherited privately, but the public version of these methods is available to call on the target node instance. Let's see how these methods can be called virtually. We can see that the pin class has a node reference here, mNode. We can see that input pin class inherits pin class publicly because it's defined as struct. So struct is essentially a class with default visibility to be public. So in this case, pin is inherited publicly and all the content of this class is public. So you can see that I chose struct here because there is no private members. This input pin class is only a decorator of a pin class. It adds extra methods on top of it. So pin class defines some methods to be protected, so they're not accessible to the user. And then you have to define a deriv class, which will define how we access them. So for example, we have a method connect, which is protected. So the deriv class has to decide how to call connect method. Let's go back to the virtual methods which were inherited privately. How are they called? As we've seen, the pin class has a member node reference mNode. And we can see that propagate backwards in the input pin is calling connected pin get owning node process backwards. Get owning node returns node reference mNode. So we get node reference and we call on the node reference process backwards. So if we have node reference, then we're calling this virtual method in a virtual fashion. But how did we get node reference from a class that inherits node privately? When the class constructor was called, the class itself has passed itself to the pin constructor, right? So it passed the reference to itself, the reference to the private part of itself, because node is inherited privately, but source node has access to its private parts. So it's passing those private parts to the constructor of output pin, and then the output pin will treat this node as a node reference, right? So even though the inheritance is private, output pin will be able to call virtual methods on this class. All right, so now we know the basics of what is going on here in this static node graph. It's not necessarily a perfect design for node graph, but the whole idea of this series is to just demonstrate you different features of C++ language. And I just want you to learn that you can actually have private inheritance with virtual methods. You can have non-virtual destructor. You can declare it protected. And here we go. This is what you can do. But now let's make this graph a little bit more dynamic. So we're going to go step by step, making it dynamic. Let's start with the basics. So this is our static node graph. Let's put it into a box. I'm going to create a box. And we call it a node graph. This box will be a node graph and will contain all the nodes. So how are we going to do that? All right, let's define a node graph class here. So our node graph class will have a set of unique pointers of the nodes. Okay? So what this means, our node graph class will have a unique pointers to each of the nodes. Okay? It will own those nodes. So we're gonna make it very simple. For now, we will only allow adding nodes. Okay? When we allow adding nodes, this situation is not gonna happen. Node will not disappear. So if we have established some connections between the nodes, they will never be invalid because nodes will never be deleted in this version of the node graph, right? So this is never gonna happen. So this problem of dangling references will not happen. Okay, so we have a small problem here, right? So this unique pointer of node will now require nodes to A, inherit publicly from node, because how else would I put nodes in this set, and B, to have virtual destructor. So let's do that. Let's just delete this comment. That's our virtual destructor. That's thing number one. And we have to put here public, okay? Because we want this source node to be publicly a node so that we can put it in a unique pointer of a node. So I'm showing this to you so that you understand why do you need to inherit publicly and how can you inherit privately. Alright, so all three node types we have here now inherit publicly from the node, and we have this virtual destructor defined here. What else do we need? We would like to demonstrate how this actually works now. So we want to put those nodes away from this main function. We want to put them into the node graph. But if we do it here in the main function, we still have them somehow, on this stack. We can access them directly. Why do we need node graph? Let's create a node graph here, and let's populate it somewhere else so that this function main doesn't have access to these concrete nodes. We're going to pass here NodeGraph reference. Okay. Now I'm going to put all this stuff in there, all of it. So that's our NodeGraph building exercise. I'm going to put here NodeGraph. Okay. So we already see that there's going to be some issue here going on. We will have to fix this. Perhaps in this iteration of our conversion from static to dynamic graph, we will return those from this function. So let's return a pair. Let it be source node int. And target node double, because this is what we have here. Okay? And now we can put something like this. Okay? So this will build us a node graph, and this will be some source node reference. We would prefer if it was just reference. How about we return here? How about we return a reference to a source node and reference to a target node? Okay, that's a source node reference and that's a target node reference. Much better. Now we need to convert this. Okay, so this transform node, put here auto transform node equals std make unique this type, okay, and we pass the fonts. Okay, that's what we're gonna do. That's our transform node. It's a unique pointer to transform node. Now source node, we're just gonna do auto source node std make unique source node, just like that. And target node, we're gonna just go and do the same. Here we go. All right. And now we probably want to change those to arrows. All right. So we're building a graph. What are we missing? We need to put those nodes in the graph. Graph, add node, source node. Okay. Now we're complaining, right? So we need to do std move. Okay. And it returns node graph. So we can continue with add node, std move, target node, and we can do add node, std move, transform node. All right, so what we have now is those variables, transform node, source node, and target node, they're no longer valid after this add node, because we moved the ownership of those nodes into the graph. Okay, so if I try to use here source node, that is gonna be bad idea, right? Because this has been moved. But what I can do here, because this is C++, I can put auto source node ref equals star source node. Okay. Okay, and then I can do auto target node ref equals star target node. Okay. And now I can just do return here, because we're supposed to return a pair of those references. Now, this is dangerous coding, right? We are returning references, raw references to something on the heap. Ooh. So it may die, for example, before we use those references. You know, they could be used after free. So that is dangerous coding. Okay? But yeah, we know that it won't happen. We know that we build a graph, we added those nodes to the graph, and they cannot be removed from the graph because we didn't define any removal methods. So because we know that we're not going to do that, we're not going to lose those nodes, we can safely assume that in this particular example, that these references are not going to go anywhere. Okay? So we have those references here. Now, again, just look at this. We said that build node graph has added nodes to the graph. There's no way of removing them, so they have to live for the lifetime of the graph, which starts here and ends in return. Those references, they cannot live any longer than that because they're defined afterwards. You cannot define them before because they're defined from the nodes that are added to the graph. So, you know, I cannot add nodes to the graph without the graph. I have to have a graph first. So yeah, so in this particular scenario, when everything lives on the stack, it's safe. Okay, so those references refer to the nodes that are on the heap, but they are managed by the object that is on the stack. If we were to create this node graph on the heap, and it would survive this main, and these references that maybe we put in some object and they survived, there would be a question whether their lifetime isn't too long, for example. The node graph could die somewhere in between, right? All right, what do we have here? Do we have a working function now? It looks like it. I don't see any errors. Let's save it for sure, and let's run g++ std equals c++20. And that's a node graph cpp -o bin node graph. All right. Bang, it compiled. Do you think it will run correctly? It didn't make any segmentation fault, so that's good. So we have 10s, 15s, 50s, 75. So remember the numbers from the last time, they're the same because we didn't change anything. So what this does, we have a function here which does 1.5 multiplied by x. It's in a transform node, so source node provides value to the transform node through the pins, and then transform node sends the result to the target node, right? So first we load the value of 10 into source node, and that gives us the result of 15 after processing forwards. And then we try backwards, so we put value 50 into source node, so that's a different value. And if we process backwards, we get 75. So that's all correct, right? All right, so that brings us to the next stage of our transformation, in which we will look into how to hide the types of those nodes, source node and target node, because right now they have a particular type. It's a source node of int. And we don't like that, right? We would like it to be some sort of hidden type, some interface maybe, you know, so that when we say load value, you know, we're calling some virtual method maybe and get value as well, you know, and maybe, you know, when we want to get data from the output pin of the source node, maybe that's not ideal. Maybe I want to have be able to get the pins of the node and say, okay, that's the input pin. Can I get the data from the input pin, you know, for printing? So let's do that. Let's do this little transformation now. All right, so now we have this static graph slightly converted into a more dynamic graph, but it's still not very dynamic. It's just, we just put the nodes into the node graph box, but we can't really do anything dynamic with them. So let's go ahead and let's do some more improvements. So now as a user, I have this node graph box, okay, this whole box. and I don't want to be seeing what's inside. So what I can do with this, I would like to have access to the source node and destination node, okay? And perhaps I want to be able to access this pin here, okay? To get the data from this pin. So maybe I want to get data from this pin. Maybe I want to load data into the source node. And maybe I want to get value from this destination node, right? So what do I need to do to get that done? So first thing we need to do is be able to find those nodes in this box. So I want to be able to say, I want to find this node. And I want to find this node, okay? So we're gonna just call them source and target nodes. So because they're specific. So in the node graph, we have some internal nodes like this one here, but we want to be able to find the beginning and the end of the graph because we want to propagate either forwards from the source or backwards from the destination, from the target, right? So we want to be able to enumerate those nodes. Right? So that's one thing. And once we have those nodes, perhaps the next thing will be to enumerate the pins, okay, so that we know what the pins are of those nodes. Let's do that. Let's go ahead and add some code. So we start by defining the pin interface, but because we have a pin class already, we will call it iPin. So this is our pin interface. It has isConnected and disconnect methods. And now into the node, we need to add some additional methods to enumerate those pins. Okay, so we have get input pins and get output pins. Okay, so that's our change to the node. I feel like the pin has an I in front, node doesn't. Let's change that node to have an I in front of it. All right, so now it's inode. So you have this iPin interface. So what's next? We probably need to make pin inherit from it. And we probably want to make it public. The isConnected and disconnect need to be implemented. We have disconnect, so we can put override. And now we need to add isConnected. All right, so this is our implementation of iPin in the pin class. And the next thing is to add the get input pins and get output pins to the node implementations. And the next thing that we need to do is to implement get input pins and get output pins for all the node classes that implement inode interface. So this is source node. Let's add implementation of get input and get output pins. All right, so we have get input pins and get output pins implemented for the source node. Let's do that for the rest of the nodes. Now we have it implemented as well for the target node. And now we have it for the transfer node. What else we need to do? We said that we want to enumerate all the nodes in the node graph. Let's add the methods to enumerate nodes. We wanted to enumerate source nodes and target nodes. One way of doing it is to enumerate all the nodes and filter by the nodes that don't have inputs or don't have outputs. So if you look carefully to this diagram, you can see that the source node doesn't have any inputs here, and the destination node doesn't have any output pins here. So this is a very good assertion that a source node would not have inputs, but then it would have outputs, and the target node would not have outputs, but would have inputs. But we need those methods added to the node as well. We've noticed that we don't have them, we need to add them. Alright, so these are the methods has inputs and has outputs in the inode. Now we need to implement them for the node types. So this is the implementation for the source node. As we said, source node would have no inputs and it has outputs. The target node, this is the implementation for the target node. It has inputs, but it has no outputs. And this is the implementation for the transfer node. It has both inputs and outputs. Alright, so we have get source nodes and get target nodes implemented. Let's go ahead and change our example to use those. So let's go back and let's see what we wanted to change here. We wanted to make source node and target node kind of invisible. Let's remove it from the return value here. And let's remove it here. Okay, so build node graph, builds the node graph, doesn't return the references anymore. So what can we do here? Okay, so we need to first find the node in the graph. How do we do that? Let's use our new methods. Auto source nodes equals graph get source nodes. That will give us source nodes. Auto target nodes equals graph get target nodes. Okay, so we have source nodes and the target nodes. Now we can check the assertion. We know that there should be only one source node in our graph because this is what we built. In this example, we have no other way of knowing which node is which. Our graph looks like this: one source node, one transform node, and one target node. On this diagram, I don't use T as target node because it will be confusing with transform node. I use D as a destination. So we have one source and one target and one transform. All right, assert target nodes size equals 1. Now, all right, so now since we know that there's only one of each of those nodes, we can do auto source node equals star std begin and source nodes. Auto target node equals star std begin target nodes. Okay, and those are pointers to inode, as we can see. Okay, inode pointer. So we also want to get the pins of the source node. For this here, get output pin, you see we need that output pin. Source output pins equals source node get output pins. Okay, and we know that there is only one, so assert source output pins size equals 1. So since there is only one output pin, we can do source output pin equals star std begin source output pins. Okay, and that gives us a pin, ipin. Now let's do some changes here. So source node process forward, that will work because this is inode interface. Okay, so that's gonna work. Load value is not gonna work. Okay, this is not gonna work because load value is not a member of inode. Same as here. Right, so we need to change this pointer to something else. We're gonna figure this out. Okay, this one here is, we know that this is source output pin. Arrow. Okay. Okay, so source output pin also doesn't have get data. Okay, so we will need to do something here. And target node get value also is not gonna work. So we have some work to do to make this work. Okay, so let's go ahead and define some interfaces. So for the source node, we're gonna define iValue loader interface, which will allow us to load value of type T into something, a node in this case. For the target node, we will define this iValue holder interface with getValue method. Okay, so that's something. We can go ahead and do some changes here. So we need value loader. So auto source value loader equals dynamic cast iValue loader of int. Okay, and that's pointer and that's source node. Okay, so we want to cast source node, which is inode, dynamically into value loader. Okay, so that may fail. So what we're gonna do is assert source value loader is not equal null pointer. Okay, now we can change this source node load value into source value loader load value, and that's fine now. And here the same. Okay, so we have source value loader sorted out. Now we need target node. Okay, so that's gonna be auto target value holder. Okay, dynamic cast I value holder double pointer target node, and assert target value holder not equal node pointer. Okay, now we can change it here, target value holder, and that's an arrow here. Okay, so we're left with this pin here, right? So we need to get this pin sorted out. How do we sort out the pin? Auto, that is a source, just call it source pin, I don't have a better idea. Dynamic cast pin of int star, okay, source output pin. We can do that because pin is a public base class of output pin, so we can do that. And yeah, we can just say source pin, okay, and the get data will work here. Okay, sounds like everything should work now, but it's gonna be a crash. Let's see the crash. How about we see the crash? Let's do that again. G++ compiles. It compiles, but it crashes. Bang, assertion failure. How did I know that? Line 354. 354, this assertion here, and probably this one here. So what we didn't do, we didn't actually implement those interfaces for those node types. Let's implement them. So we need to implement iValue loader for the source node and iValue holder for the target node. So this is our source node. Let's add here public iValue loader, okay? But that's not all. We need to implement load value. This is the wrong load value. We need to change it. Yeah, so this is a template. So this is not gonna implement a virtual function. Let's implement virtual function instead of this, because you won't be actually using this anymore. All right, let's replace it with a correct implementation of the virtual method. It's essentially the same function. It's just no longer a template, and this is no longer forwarding reference. Okay, now this is just an expiring value. Let's implement iValue holder for the target node. Public iValue holder, but we need to say type T, you know, and I think this is what we didn't do here. Oh, and now it's correct. Now, why is it black? I don't know. Why is this class black? I don't know. The highlighting here in VS Code is not perfect, but okay. Now, this get value needs to be changed to be an override. All right, that should have worked. Now, let's see if we can compile our code. It does. Okay, well, if we can, let's see if we can run it. We can. So in this iteration of our migration from static node graph into dynamic node graph, we added dynamic enumeration of the nodes. We can see it here. We added dynamic enumeration of the pins, and then we added the dynamic interfaces for those nodes so that we can access some information without knowing the exact type of the node. In this case, iValue loader and iValue holder. All right, so we made a C++ node graph dynamic, a little bit more dynamic. We put it into the box. We enumerated the nodes and pins. How about we're gonna go ahead and see if we can do the same in Rust? Can we even do that in Rust? So this is our Rust code so far, and we have noticed maybe that there's a lot of those lifetimes A. Let's get rid of those lifetimes. We don't need them. So graph node doesn't need the lifetime here. Okay. Graph node pin does. Okay. So I probably need to explain to you how those lifetimes work. So on some example maybe. So let's say I have a struct here, okay, some struct foo with some I32, okay, so that's my simple struct. Now I have a struct here, bar, okay, and this bar has a reference to foo, okay. Now it is a reference. If you just do it like this, it's not going to be happy, you know, the roost will complain when you do that. Will say, you need to give a lifetime. So you give it some lifetime, you can give it a lifetime A. Okay, so this lifetime A is just, you know, exactly what is it? It's undeclared lifetime. You need to declare it, and in order to declare it, you need to put it here, and to say that struct bar contains lifetime A. This triangle brackets and lifetime means contains. It's a contains lifetime. It's not a lifetime of bar. So what happens when you actually create a struct bar? So let's create a function bars. Okay, and it will create bar, but bar needs a reference to foo. So okay, so let's start with bar. Bar equals bar, and then we don't know what. We need to put here b something. What's b? Okay, so maybe we need to define this b. Okay, let foo equals foo. Okay, and foo has a, and that's an integer. Let's say 5. Okay, so that's our foo. Now this can be b is a foo like this. That's all okay now. Okay, it's all okay. Now you may wonder, how is it okay? I didn't specify this lifetime here. It says underscore, so the default lifetime, the implicit lifetime. How does this work? So we're creating foo here, so that's clear, right? So this is some struct foo created on the stack. It is in some address on the stack. The stack is, you know, the stack frame exists for this scope here. So this scope starts here, and everything that's defined in this scope lives somewhere in this stack frame. Okay, so in this stack frame we have a foo, and it takes 4 bytes because it's an int32. So some 4 bytes in this stack frame live in this stack frame, and the lifetime of this 4 bytes is the lifetime of this stack frame. So the moment when we go back to whoever was calling this function, the stack frame will be gone, and everything that was on that stack frame will be gone. Now bar is a struct that references foo, and it references something with lifetime alpha, which means that this foo leaves some amount of lifetime. Okay, and we know that in this case foo leaves the amount of lifetime of that stack frame. Okay, so you know, so we know that the alpha has some duration of the lifetime, right? Now the question is, what is the lifetime of the bar? Because bar has its own lifetime, and it's not alpha. So you can assume that bar lives beta lifetime, and I can show you that. I'm going to create here a function, okay, that takes foo. So that will be a fuzz function, and it's going to be taking reference of lifetime alpha to foo, okay, and that's going to be some foo. Okay, so that's our fuzz function. Now we're going to move this bar into that function. Okay, so we're going to define it like this. Okay, so what happens here, we have undefined lifetime alpha, because this alpha here is local to this function. So we have to say alpha here, okay? All right, so what happens next? We want to call fuzz. So let's call fuzz with foo, okay? So we're passing foo to the fuzz, okay? So let's think about what are the lifetimes here. So let's call them by some names, okay? So the lifetime of the bus frame is gonna be, let's call this lifetime monkey, okay? And the lifetime of this stack frame, let's call it elephant. Okay, so we can clearly see that the foo on the stack, so this, let's call this stack frame monkey. Okay, so we have a stack and we have a monkey frame, and on top of this we have an elephant frame when we call fuzz. So if something lives in the monkey frame, it lives longer than something that lives in the elephant frame. We can agree on that, right? So we can see that this foo lives longer than this fuzz. Okay, because I can, for example, here do something with the foo. I can do foo something, you know. I can even make it mutable maybe. And maybe I can do foo a equals 10, you know. I can do that. So you can see that the foo has lived longer than the fuzz. Okay. And I have changed the foo afterwards. Okay. So here's what happens here. So when we have a struct that has a reference inside, we need to say how long this reference is going to live. And for example, in this case, we're going to say the reference inside the struct will live alpha amount of time. Okay. So this says I have inside of me a reference that will live alpha amount of time. Myself, I have to live shorter or the same amount of time. I cannot outlive what I have reference to. If I live longer than the thing I'm referring to, then I'm storing a dangling pointer. Okay? If this reference was living shorter than the bar, then it becomes dangling reference. So in this case, it will not become dangling reference, and Roost knows very well that this is not going to happen because Roost knows that the frame monkey lives longer than the flame elephant. And in this case, bar's lifetime is elephant, and the lifetime of this underscore is the lifetime of this underscore of this foo is monkey. Okay? I hope this explains everything. I can draw you a picture if you want. So this is our stack, okay? And this is our stack frame monkey, and on top of this is elephant. And somewhere in the monkey there is 4 bytes, which are the foo, and somewhere here in the elephant frame there is probably 8 bytes, a pointer pointing to those bytes here. Okay, so stack grows this way. So when we exit the function, we go this way, and this is gonna disappear. So this is valid. Okay, having a variable on stack that points to something that's on the frame below, it's fine because this frame is disappear after this frame. But having this the other way, so if I were to have something here, and something here would be pointing to this in some magical way, then when this frame disappears, this becomes a dangling pointer, and this is what Roost prevents. You cannot have that in Roost, okay? Well, not in the safe mode Roost. In safe mode Roost, this is not possible. Now, what is possible is something else, and this is actually interesting. So you may have some stack frame, you may have some variable on the stack frame, and in the same frame you can have a reference to this variable. And in this case, both the reference and the variable have the same lifetime. So this is alpha lifetime, then this is also alpha lifetime, you know. Whereas in this case, this is alpha lifetime and this is beta lifetime, different lifetimes. And in this case, beta lifetime is shorter than alpha lifetime. Okay, so this is less than alpha, and it is invalid here because we have a pointer in alpha that points to something that lives in beta. So that's not legal. Here, this alpha lifetime, this is beta lifetime. So in beta lifetime, which is shorter than alpha lifetime, we have a pointer to something that lives alpha lifetime. So that's okay because this pointer will stop living before this thing is stopping living. And here, both pointer and the thing that it points to, they live the same amount of time. Okay? So that's very important to understand here. Alright, so how do we get this static node graph into dynamic form in the same way as we did in C++? So we can create a node graph container for the nodes, and it can point to those nodes using, we can put them in boxes. Okay, Rust has a thing called box. But let's see how wrong this will go. If lifetimes are not needed to specify, let's remove them. Let's keep only the ones that are actually needed. So let's analyze. This graph node pin needs a lifetime because it contains a lifetime, right? So this ref cell contains a reference to that graph node, okay? So this graph node does not take lifetime anymore. We just removed it, okay? Yeah, so we can just do this. So we have a reference to a graph node. So graph node itself doesn't contain any lifetime dependent things, but we have a reference to a graph node, and that reference needs to know how long will the graph node live. So this is how we say that. So this reference alpha lifetime graph node says how long is the graph node gonna live, okay? But the graph node itself, it doesn't care how long it lives. Everything that happens inside of the graph node is, living the same amount of time as graph node. So we remove the alpha lifetime from the graph node because graph node doesn't depend on lifetime here. The graph node pin, so we remove this lifetime here from graph node, but we still have this lifetime of this reference to the graph node because graph node itself may live some lifetime, okay? And our reference needs to have the lifetime so that whenever we use graph node pin, we know that this graph node pin contains something that can live some amount of lifetime. The connection is essentially a reference to a pin. So it's a pin-to-pin reference. So this pin has its own lifetime, but it contains a reference to another pin, and this is the lifetime of that another pin. And we're saying that this another pin has to have the same lifetime as the graph node. Let's look at the picture and see why is that. And that's not obvious. So let me explain you this complicated situation. So we're saying that this pin has a reference to this node, and we're saying that this node has a lifetime alpha, okay? And we also know that this node actually contains this pin. So this pin also has lifetime alpha, which is not something that we can tell the pin, okay? So this pin doesn't know anywhere here what is its lifetime. That's the reality here. This graph node pin has some lifetime, it doesn't know what is its lifetime. It's a struct. Yeah, but there is a connection here to this pin. So why does this pin have to leave also alpha lifetime? Well, if there's only connection in this direction, maybe it does not need to leave alpha lifetime. Maybe it needs to leave some beta lifetime. But because this pin will point back to this guy, they just have to have the same lifetime. The whole graph needs to have the same lifetime. Just imagine what will happen. If I'm having this node pointing to this node and this node pointing to this node, I cannot make any of these nodes disappear at any other stack frame than the same stack frame. They have to be in the same stack frame. This node, this pin in this node cannot be pointing to a node that is in a different stack frame in this model, okay? Not with the references. We would have to go down and use some other type of pointers in Rust to allow this to happen, to be more dynamic, to be able to add nodes, add connections dynamically at runtime. We cannot do that with lifetimes and references like this, right? Because imagine what happens when we just say, okay, this node goes away, this pin goes away. What happens with this reference? So in Rust, I'm afraid that we will not be able to achieve this stage of development of our static node graph to dynamic node graph migration. So we will probably do some more involved work on the Rust side. So in Rust, it is not really possible to achieve the same result as we did in C++. That is to put nodes into a container and keep the references as connections, because the lifetime checker in Rust is gonna prevent us from doing so, okay? In Rust, because of strict lifetime rules, we can't really go this path of doing this step that we're gonna put those nodes into the boxes. We have to rethink all the nodes, and we have to rethink how our node graph will be constructed. So we will definitely use something like arc or RC. We will see what we're gonna use, because, for example, if I were to use arc, and that's gonna be like a teaser for the next episode, if I use arc, so actually there is arc new and there is cyclic, you see, and arc new cyclic gets me in here, and I can do that, and then some node, I want a source node. Of course, I will not be saying that I want lifetime, because I'll have to remove it from there. I have to remove the lifetime. I just want to say source node default, okay, and that's gonna be my that's gonna be my thing. And in the source, instead of this lifetime, I'm just gonna have source node in i32, okay, and somewhere in my source node I'm gonna have my output pin, where I'm gonna say pin, okay, and then in the pin I'm gonna say node is me, okay, but node in this case is a reference, and we will have this weak, and this will allow us to to avoid lifetime issues. We'll have the arcs and the weak tracking of objects, and this way we will avoid issues like that. All right, so that will be for the next episode, and now thank you so much for watching, and stay tuned. On the next episode will come, and yay, we did it. See you soon.